All right, so this will be, I believe, the second to last post that I'm going to have of new material. And we're going to go through in this one the derivation for the sort of calculation of the critical buckling load for slender columns. And so to do that, we're going to use something called the equilibrium method. And if you remember, in the previous lecture, we defined buckling, or the sort of that buckling limit, as the point where the moment that causes the displacement is enough to maintain that displacement. So effectively, I provide a certain axial force in a member, and as that member sort of begins to kick out to the side, that axial force is sufficient together with that delta to maintain the deformed shape, right? And that's sort of what that, if you remember that table where we first applied the axial force, then we applied a lateral force, right, that sort of kicked it out slightly. And then when we removed that lateral force, the column stayed in a deformed shape, right? And that's sort of what we defined as the sort of the definition of the buckling load. So let's take a look here at, so this will be an originally straight column, right, that will look like this. And then it buckles, right? And this guy we're going to say is P critical, right? And the length of the column, we're going to define as L, like that, right? And then what we're going to do is we're going to take a cut, right? Just like we had been doing previously. I'm going to now define a coordinate system that looks like this. So this is the x direction and this is the y direction. Again, the x direction is going along the column. Right? And let me do, I guess we'll do blue here. So the deformed shape is going to look something like this. Where this guy here is the support. Right? And then here we've got a downward force here, and we've got a moment. Right? So this downward force we're going to call P critical. And this moment is just a moment of the moment caused by P critical coupled with the deformation. Right? So this deformation here, in fact, let me do it like this. So this deformation here, in fact, let me do it with green. So this deformation here is the deformed shape, right? So this guy is the lateral deformation. So this is the lateral deformation. And it is also what you guys had solved for as the elastic curve, right, previously. Now that wasn't with columns, it was with beams, but effectively what it was the deformation caused by a moment on the element, right? So in this case, it's a column. There's a moment on the element that's causing a flexural deformation, right? That's exactly the same thing as turn it sideways, and we'll call it a beam, right? But effectively nothing changes there. So let me just put this P critical here as well, right? So you can see those two P criticals are offset by this V of X, right, the deformation. And so the moment is going to have to account for that, because right now you can see those axial forces are actually trying to spin trying to spin the element in the counterclockwise direction. And so that moment has to come back and maintain equilibrium. Right? And so if we, sorry, I'm a little frog in my throat here. Okay, so the actual force, or the moment, sorry, is, and I'm going to sort of drop the P critical for now, but we'll bring it back. I just don't want to keep writing it. So the moment throughout this column is just the P, right, the axial force that's on the column, times that deformation. And so at the ends, at the top at the roller support and at the bottom at the pin support, there is no moment, right, because there's no eccentricity, there's no deformation of the column at that point, right? And in the middle, where the deformation, lateral deformation is the maximum, that's where the moment is also going to be a maximum, right? So this d squared v dx squared is just going to equal moment over EI, right? And that is going to equal P v of x over EI. Right? And this is where we start to get a bit of a weird, I shouldn't say weird, it's simply a different, sort of scenario than we have looked at before, right? And that's a scenario where the load, right, in this case the moment, is also a function of V, right? So I can't, it's not independent of the deformed shape, it's directly related to the deformed shape, right? So if I rewrite this now, it actually looks like this: d squared v dx squared, right, plus p divided by EI times v equals 0. Right? And because we have this second v there, right, because the moment is a function of the deformation, more moment, right? Less deformation, less moment. So there's some coupling between the moment that is driving the deformation and the deformation itself, right? So this, if you go back to your class in ordinary differential equations, has a sort of a very common type problem, and it also has a very sort of common solution, which is sine C1 sine, this will be the square root of P over EI times x plus C2 cosine square root P over EI times x. So if you go back and take a look at sort of this generic form, this guy here is actually in the square root, right? So whatever is in there in the generic problem just gets dumped into that square root. And you can, so the way to verify this is just take the second derivative of that v of x, right? And then plug it into this equation here, and you'll see that it will satisfy that equation, right? So you take the second derivative, everything is multiplied by a minus, P over EI. Other than that, it doesn't change. And then that first term will basically reduce to a minus, P over EI plus P over EI. And what those terms are multiplied by are just the inside here, right? So that's C1 sine, C2 cosine, etc., right? So they all cancel, right? So this is the solution to that differential equation. And if we look at the boundary conditions, the first one is that at v equals 0, we get 0, right? So that just basically says that the deformation here, right, at the pin support is 0, right? And if we look at the second one, which is v of L, that is also 0. So that tells me that the displacement at the top end, at the roller support, is also 0. So the first one is fairly straightforward. If you plug in 0 for all of these things, you're going to get that C2 times 1, because the cosine of 0 is 1. The sine of 0 is 0, right? So that term drops out. And so that gives us that C2 has to be 0. Right? So we're left with this guy, that the V of L, which is now just C1 sine square root P over EI times L, that has to equal 0. Right? Now it turns out that has a bunch of different solutions. Right? In general, there's 2. Right? So I can set C1 equal to 0. Right? And this is known as, if you guys remember this, it's known as the trivial solution. Basically what it says is if there's no displacement, because if C1 is 0, then the entire displaced shape is 0, so it doesn't displace, then there is no moment, right? And if there's no moment, then that's not causing the displacement. So that is a legitimate solution. It doesn't really tell us anything. That's why it's called the trivial solution. So the other solution that is more interesting is when the displacement is not 0, right? So C1 is not 0, which means that this sine of square root P over EI times L, that has to equal 0, right? And when does that equal 0? Well, that equals 0 when this square root P over EI times L equals pi, right? 2 pi, 3 pi, etc. Right? So that sine of square root P over EI times L will equal 0 as long as P over EI, square root P over EI times L equals pi, 2 pi, 3 pi, etc. Because we know the sine wave is 0 at those locations, right? So if we sort of keep moving forward here, we're going to say that the square root of, now I'm going to bring the P critical back, because this is now the buckling load. I mean, I guess it always was the buckling load, times L equals n times pi, right? And if we then solve for P critical, we get n squared pi squared EI divided by L squared. Right. I'm going to box this guy in red. Right? So that is our buckling load, right? If I give you a column, right, and you want to calculate the lowest buckling load, right, and so here we would say that n equals 1, 2, 3, all integer values, right? If n is not a round integer, then that P critical would not cause this term here to go to 0. So it would not satisfy the equilibrium equation, right? So, so it has to be 1, 2, 3, right? And n equals 1 is the lowest buckling load, right? So that, in general, is what we care about, right? I don't care if this thing is going to buckle at a higher buckling load, because once I get to P critical equals pi squared EI over L squared, meaning n is 1, then the structure's already buckled, right? So if I'm going to draw kind of what happens here, right? Let me draw a few of these guys. Right, so this one, the first one here, so let's say these are all L. All right, and this last one like this. All right, so we have 3 columns here, right? So the first one will buckle. In fact, let me do this in red. So we'll buckle something like that, right? And in this case, n equals 1. So you can think about n as the number of half sine waves in the buckling shape. Okay? So in this case, P critical equals pi squared EI over L squared, like that. Right? Now, if I come into this same column and I put a new support here, right? Now I can't buckle in the first mode, as it's called, right? And the reason I can't buckle in the first mode is because I'm restraining it, right? That where that roller support is in the middle, that used to be where the maximum displacement was, right? But I'm restraining that, so that can't occur. So the only way this guy can buckle is something like this, right? Oh, got to turn that guy off, sorry about that. So it can buckle something like this, right? And so now n equals 2, and this deformation here is 0.5 L. Right? So if I'm going to calculate P critical, right, and there's sort of 2 ways you can do that here. I can say, all right, well, P critical equals, this is the second buckling mode, right? So n is 2. So if I plug in n equals 2, I get something like this over L squared, right? Let me just rewrite this one here as well so it's a little bit neater. Right? So there's 2 ways to consider this, right? N equals 2, and that gives me that 4 out top, right? Great. The other way to think about it is n equals 1, but this is the new length, right? So if I just plug in, instead of the full L, I just plug in 0.5 L, right? Then you see what happens is that 0.5 is squared, so it becomes 0.25. When I put that in the numerator, it becomes 4, right? So you can either do it based on, you know, this n value, or we can just decide that the length is actually the length over which a half sine wave occurs, right? And then I don't need to worry about this n any longer, right? So let's just show that that actually kind of holds here. So in this case, let's put a couple more supports, right? And now the buckling load or buckling shape is going to look something like that. Now the length over which the half sine wave occurs is just L over 3, like that, right? And we see that n equals 3. Right? And so now my P critical here is 9 pi times EI divided by L squared, right? And you could say, okay, well, that 9 is actually the 3 squared, right? And there we're following this equation up top, right? Or I could say, no, this isn't the third buckling mode. This is the first buckling mode, but it's going to occur over a length of L over 3. So if I square that, it just becomes L over 9. The 9 comes to the top. You get exactly the same thing, right? So whether or not you decide to look at the different buckling modes, n equals 1, 2, 3, right? Understanding that n is the number of half sine waves that will occur, right? Or you're going to simply refer to it as the first buckling mode, and then the question is just, what length do I want to use, right? What length will that half sine wave occur over, okay? So let me jump into and sort of put maybe a finer point on this, right? So this will be for boundary conditions. So BC in this class is always boundary conditions. Other than simply supported. Right? So now what we're going to do is I'm going to take that P critical equation, right? I'm going to drop the n, right? And in the denominator, I'm going to change the L to a KL, right? Where the KL is the effective length. Right? And that's the length over which a half sine wave can develop, right? So this is the length of a half sine wave. Right? So it depends clearly on the boundary conditions, right? So let me draw a few examples here. So let me get this guy. We'll put one here. We'll put one here, and then we'll put one here. All right. So this first one, this is all length L, right? So this is L. So for the first one, we're going to call this simply supported, right? Like that. And here, just as we've been doing, that's my half sine wave, right? So my KL just equals L, right? So therefore my K equals 1.0. Okay. All right, so now let's take a look at this guy. And I know this is going to look a little strange to you because I'm putting fixed supports on there. Just understand those fixed supports will not restrain axial. So that's why I can put an axial force on top of that fixed support, right? And it still gets into the column. Right. So here, the deformed shape is going to look something like this, right? Oh, forgot forgot about that. Okay, so it looks something like this, right? So that is my buckled shape now. And I guess I can do it in green. There is a location here where this guy is basically a half sine wave, right? So that here is KL equals actually 1/2 L, right? And so in this case, K equals 0.5. Right? So you can see these are inflection points here, right? That's where the buckled shape goes from being, sort of concave to the left to concave to the right, okay? So next one that we're going to do looks like this. Then it has a fixed support here, right? And so this buckled shape looks something like this. Did it again. So it looks something like that. If I'm going to highlight sort of in green the half sine wave portion of it, it looks like that, right? And the dimension here is KL equals 0.7 L. So in this case, K equals 0.7, right? And then the last one that we're going to discuss looks like this, right? And now I'm going to put my axial force on top. And now, this is interesting, the buckled shape looks like this, right? So that's not a half sine wave, that's a quarter of a sine wave, right? So I can continue that down, 1, 2, 3, 1, 2, 3, like that, right? So this here is now KL, and that equals 2 times L. So in this case, K is equal to 2.0, right? So this is a much more sort of powerful way to make use of the buckling equation, right? So we define this effective length term, K, that goes from 0 to, I guess it can probably go to just 2. I think 2 might be the maximum. These are the only cases that we're going to deal with, right? So simply supported, that's just a single half sine wave. Fixed is just half of the length is the half sine wave. The propped cantilever, so roller fixed, that's 0.7. And then if it's just a cantilever beam, it's 2.0, right? So if you identify the length over which a half sine wave will occur, then you can go ahead and compute the buckling load regardless of the boundary conditions, right? Okay, and so then the final thing I want to do in this lecture is kind of revisit something I had mentioned earlier, and I want to define something called the critical stress. So this is the stress at which buckling occurs. Right. So what we've done so far is we've calculated P critical. That would be the force at which buckling occurs, right? So what I want to do here, and there's nothing, magical or shouldn't be terribly confusing about this, but basically the P critical sigma critical, the stress at which buckling occurs, is just the P critical divided by the cross-sectional area, right? But I want to show you what happens because for whatever reason, people like to go to, in some cases, great lengths to make things, I think, a little bit more complicated than they need to be, right? So all I'm doing here is I'm plugging in the P critical, right? That's, drop my pen. That's this term here, right? That's P critical, right? I'm dropping the KL, but you could just replace, L with KL, right? And then I'm multiplying it by 1 over area, right? So same as dividing it by the area. And then I'm going to rearrange this a little bit, right? So I'm going to get pi squared, E over L squared. And then this term here now becomes I over A, right? And that, if you remember when we first started talking about this, was the radius of gyration. Like that, right? So I over A is R squared, right? R being the radius of gyration, right? So if I substitute that in, right, I'm going to get pi squared times E divided by this L divided by R squared, right? So the R is now underneath the L, right? And then we defined that earlier as the slenderness ratio. Right. So L over R is the slenderness ratio, and it is related. So a lot of people have reduced this because it turns out that aside from the elastic modulus, right, which is sitting right there, that the slenderness ratio is really the metric, if you will, or the characteristic of a column that governs how and at what load it's going to buckle, right? So it's basically the length, or we should say the effective length. So again, that L can be written as KL, right? If it's simply supported, it's just L because K is 1, but you can substitute in those different boundary conditions. And then you're going to divide that by the radius of gyration, right, which is the moment of inertia divided by the cross-sectional area. And in the steel manual, when you get to steel design next year, you will see that they actually tabulate these values R, right? So you can just go in there and pull it for any cross-section, right? In fact, I think they even tabulate the slenderness ratios for simply supported columns, right? So that's how, when you start to relate, this sort of buckling as a limit state and how it's used in design, right? The big thing is that they define it based on a buckling stress, not a buckling load. So that means they've got to divide it by the cross-sectional area. And then they sort of rearrange these things, defining both the radius of gyration, right? That's the R term. And then ultimately the slenderness ratio, which is just L over R, right? And that's how they sort of tabulate these designs. So fundamentally, it's nothing different than this equation right here. In fact, let me sort of box this guy as well. So it's not fundamentally any different than that equation. The only thing that's different is I'm dividing it by area and we're reporting it in terms of stress, right? So we're not going to use critical stress here. I'm just going to be asking you to calculate the buckling load, because I think that's a little more fundamental. But just so you know, moving forward, if you want to come back and revisit these notes when you get to steel design, this will probably fill in a lot of gaps for you. So, all right, so that's it for this lecture. We have one more where I'll do a couple examples.